Okay, welcome to another video. So what I want to do today is just go through the carbon cycle, which is the next of the biogeochemical cycles. Similar sort of format to what we did for the nitrogen cycle. We'll kind of build up a big diagram. Before we talk about that, just hopefully the nitrogen cycle stuff made sense. There is quite a nice question which you could have a go at in your resource booklet. It's on page 63. It's got a picture of a student and a rat. It's a bit of a bizarre question, but I would like to maybe have a go at that. We can perhaps talk about that in the live session we hold later this week, so that's worth a go. Just make sure for the nitrogen cycle that you have made notes. Not only have you drawn out the cycle, but you've also made notes on the human impacts on the cycle and also how we can manage the cycle more sustainably. I did put the sustainable management of the cycle in the email I sent you a few days ago, so just make sure you got those notes. Also, there were a few past paper questions which we sort of went through in the live session, so again, just make sure you've written out those notes, you've had a look at the mark schemes, you've checked your answer, you've added any additional points in a different coloured pen, etc, etc. Anyway, today we're going to talk about the carbon cycle. Now I'm going slightly out of order compared to the PowerPoint on the Moodle site. On there, the next one's the phosphorus cycle. So the slides to do with the carbon cycle start on page 21. Most of them are to do with the human impacts. So you could have a look at the first, I think, couple of slides, which tells you about sort of why it's an important cycle and where the main stores are. So the key thing about the carbon cycle is it's normally in a state of dynamic equilibrium. If you remember, dynamic means constantly changing, equilibrium means overall staying the same. So there is a name in environmental science for things being kept in balance. Dynamic equilibrium, you can say also things in a state of homeostasis, which is the same thing. You can also talk about the idea of Gaia theory. You might remember when we talked about James Lovelock, who had this idea of the Earth being sort of in this sort of permanently self-regulating system. It's the Earth being able to sort of balance things out naturally. That's kind of Gaia hypothesis. So the carbon cycle is a good example of that, where normally the amount of carbon dioxide, for example, in the atmosphere is roughly kept in balance. There are some processes that remove carbon dioxide from the atmosphere, such as photosynthesis, and there are other processes that return carbon dioxide to the atmosphere, like aerobic respiration, and overall the amount stays the same. Obviously, we are changing the natural balance of the carbon cycle. That's global climate change, isn't it? And two of the greenhouse gases involved in global climate change contain carbon dioxide and methane. So very relevant to the carbon cycle stuff. So why is carbon important? Well, it's the only element that's able to build up long chains of atoms, things like carbohydrates. So it's a very important energy source for organisms. It's obviously vital to photosynthesis as well. So a really important element. Okay, so what I'm going to do for the rest of the session is I'm going to turn the camera around. I'm going to try and draw out the diagram using a slightly different camera angle. It was very difficult to actually write on it when I had it set up as I did last time. So just bear with me a second. I'm going to move the camera around, and what I'd like you to do is watch the video, have a look at how I'm drawing out the cycle, get your head around it, and then I'd like you to draw your own version. Again, using an A3 ideally if you've got it. If you could do it on A4, just keep your writing quite small. So watch it first, and then hopefully when you've kind of got your head around it, and of course you can have a look in your textbook as well. So on page 123, 124, I'd like you to have a go at drawing it out yourself. Okay, so I'm going to move the camera. Alright, so what you can see here then is the carbon cycle. So I've drawn it out. Again, this is in cross section, so this is the atmosphere and this is the land. I've also put the ocean on as well. So you can see a few different things on here. Let me just get rid of some of these arrows. So we've got a volcano, hard to believe, but it is a volcano over here. We've got a forest. We've got some kind of food chain happening here. We've got dead organic matter, and we've got some phytoplankton here in the oceans. We've also got some fish, and we've also got, by the looks of it, got some dead fish as well. So if we start off thinking about where carbon is stored, well, some of the carbon is stored in the oceans, and it's stored as hydrogen carbonate ions, or dissolved CO2, you could say. I haven't actually written that on here, I haven't got a lot of space on here, but you could write in some of these stores. So hydrogen, carbon, ions, or dissolved CO2 is the store in the oceans. You've also got carbon stored in dead organic matter. Again, all these stores, it's a good idea to put a box around them. Carbon, of course, is stored in living organisms. There's things like lipids and proteins. And of course, we've got carbon also stored in the atmosphere. And finally, we've got carbon stored deep underground in things like carbonate rocks, so things like limestone and things like fossil fuels as well. So lots of different stores of carbon. So I guess one of the first things you could put on a carbon cycle diagram is carbon dioxide in the atmosphere. And hopefully you remember what the concentration of carbon dioxide in the atmosphere is, which is about 400 parts per million, or 0.04%, depending on which way you want to write that. So normally the amount is kept in balance, and we've got the process of respiration and photosynthesis. Again, I'm not going to label those on here, I'm going to run out of space, but on your diagram you can be labelling those arrows. And there's that natural exchange, those things naturally kept in balance, photosynthesis equaling respiration. We've also got a food chain here. So we've got some vegetation, we've got herbivores, maybe carnivores, and then again you can show how carbon moves along food chains as carbohydrates, lipids, proteins, things like that. Obviously when things die, we've got excretion as well, but also when things die, dead vegetation, dead animals and excretory wastes, those are going to go down into the dead organic matter store in soils. Now what happens to that dead organic matter? Well, if it's aerobically decomposed by decomposers, detritivores, decomposers, if that's aerobically done, that will release carbon dioxide back to the atmosphere. So you could label along this arrow aerobic decomposition, and that would be returning CO2 to the atmosphere. On the other hand, if it was anaerobically being broken down, anaerobic decomposition, then that would return methane to the atmosphere, methane being CH4. And that methane, that CH4, would normally oxidize at some point to carbon dioxide. So we've got methane being returned to the atmosphere, CH4, and we've got carbon dioxide, depending on whether it's aerobic or anaerobic decomposition. Of course, not all dead organic matter is decomposed. You remember from West Hay Moor, in very waterlogged environments, things like peat start to form, and eventually you can get the formation of fossil fuels. And this is one of the really long-term permanent stores of carbon. So you could label, this is a sort of process of, I think they call it, let me just check in the textbook, I think they call it sedimentation, but let me just double check. It's been labelled a few different things. Or fossilization you could call it as well. Fossilization probably is a better term to use. So fossilization would be when dead organic matter doesn't break down in very anaerobic waterlogged conditions and would form fossil fuels. So that's most of the sort of land side of the diagram completed. We've got over here a volcano. Of course, volcanoes also emit carbon dioxide. That's another natural source of carbon dioxide going into the atmosphere. If you want to as well, you can have a very dramatic forest fire happening maybe somewhere on your diagram, which naturally occur. Again, that is going to be returning carbon dioxide back to the atmosphere. So we've got processes that are taking carbon into the soils and rocks, and we've got processes that are returning it, and those things being kept roughly in balance. Okay, so in the oceans, of course, we've got something similar happening, maybe just a little bit different. So in the oceans, we have a natural balance going into and out of water. So some gases dissolve into water, so we've got some carbon dioxide from the atmosphere dissolving into oceans, and we've got some carbon dioxide coming out of solution back to the atmosphere. And when things come out of solution, it's called exsolving. So exsolving out of the oceans and dissolving into the oceans. And then within the oceans themselves, of course, we've got, well, you could label on here, in fact, I did say earlier, you can label the store of carbon in the oceans. I haven't really got, perhaps put it here. So you could put a little box here and you could label the store of carbon in the oceans. That would be dissolved carbon dioxide, or you could write hydrogen carbonate ions. It doesn't matter, that's the form it's stored in the water. So of course here we've got our phytoplankton, and again you could be showing this idea of respiration and photosynthesis being in balance. Phytoplankton absorbing carbon dioxide from the water that's dissolved in the water and the photosynthesizing, but also returning carbon dioxide to the water when they're respiring. And then you've got exactly the same thing. We've got our food chain or food web. Again, exactly the same as the land-based one between the phytoplankton and fish. And again, we've got excretory wastes, we've got dead fish, and everything in the oceans ultimately descends back towards the ocean floor. Now that build-up of dead organic matter in the bottom of the oceans, what happens to that dead organic matter down here? Well, some of it may decompose, and if it does decompose, it will become dissolved into deep oceans. So there is carbon that's found in ocean waters, dissolved at great depths. So some of this may decompose, but the majority of this dead organic matter in those very cold conditions at the bottom of the ocean doesn't decay, doesn't decompose, and actually what happens over time is it forms carbonate rocks. Now you might be able to think of a carbonate rock. So we're talking about rocks that maybe build up from the remains of dead sea creatures, exoskeletons and bones and things like that. So limestone would be a very good example of a carbonate rock. So this is a process of sedimentation, the build-up of sediments on the ocean floor, not decaying, not decomposing, and over millions of years forming carbonate rocks like limestone, which is the biggest store of carbon in the world and also the longest, most permanent store of carbon. And that essentially is the carbon cycle. So normally kept in a state of dynamic equilibrium. Obviously our actions are starting to change that, but for now all I'd like you to do is try to draw out your own version. I'd probably recommend starting in pencil first. As you can see, it's quite difficult to work out how to set it out to fit it all in, but if you can have a go at drawing that out in detail, having a read in the textbook, page 123 to 124, and we can talk more about the carbon cycle in our next live Teams meeting later this week.